Hello friends, so today we are going to solve the questions from the year 1999 and they are total of 5 questions from the year 1999. So in the first part, or the first question, it is given that a concave lens of glass, refractive index 1.5, has both surfaces of same radius of curvature r. On immersion in a medium of refractive index 1.75, it will behave as. So we have to find out whether it will be convergent lens of respective the focal length, or it will be a divergent lens with the same focal length as for the convergent. We have to find out both whether it is convergent, as well as we are going to find out whether it is what is their focal length in terms of radius for curvature r. So we are given that the refractive index of the lens is given to us. So we can write refractive index of the lens, it is our 1.5, and refractive index of the medium is given as 1.75. This is given as 1.75, and the radius of curvature of both you can say surfaces is given as r. So we need to find the first of all we can say focal length. So we can use the basic formula, which is our lens maker formula, and we can say that our 1 upon f is equal to we can write a ratio of refractive index of lens to medium minus 1, and it will be 1 minus 1 upon r1 minus 1 upon r2. And in this case both surfaces are having same radius of curvature, therefore we can write that our r1 will be equal to minus of r and our r2 will be equal to r. It can be true reverse also, r2 can be minus of r and r1 will be plus of r, it doesn't matter. So we substitute the given values, and for this we are going to get this as 1 upon f is equal to 1.5, and this is 1.75 minus 1, and we get 1 upon minus 1 upon r. So we can easily write that our 1 upon f will be equal to 2 upon 7r, or from here we can say that our f will be equal to 3.5 times r. So at least for the focal length we are clear that it will be 3.5 r. So either option A will be correct or option B will be correct. Now we come to the convergent part or divergent part. So from here we can clearly see that our focal length, that is our f, it is positive. Therefore it is going to behave like a converging lens. So we are going to have a converging lens. So therefore option number A is the correct one. You can say option A is correct. Come to the next question, and here it is given that a yellow light is used in a single slit diffraction experiment with a slit width of 0.6 millimeter. If the yellow light is replaced by an X-ray, then the observed pattern will reveal. Okay, so we have to find out what will be the basically the pattern that will be associated with the when yellow light is replaced by the X-rays. And you can say that the important thing here is to remember that the diffraction pattern, which is based on the experiment of this diffraction experimentation, herein it only occurs when the wavelength of the wave is comparable to the size of the aperture. Okay. So we can say that diffraction occurs when the wavelength of the wave is comparable to the size of the aperture. And aperture here is basically slit width because it is a single slit experiment. So it is a slit width and suppose it is given as A. So it means for diffraction the wavelength should be approximately same as our size of the aperture. And the wavelength of, you can say, our yellow light you can say wavelength of yellow, it is approximately is our 580 nanometer, or also we can say this will be 5.8 into 10 to the power minus 7 meters. And the aperture width, that is our A, is given to us as 0.6 millimeter, 0.6 millimeter, or we can say this will be equal to 6 into 10 to the power minus 4 meters. So this both is, you can say, comparable to each other. So because of that, the diffraction is taking place. And now it is replaced by the, you can say, X-rays. And for X-rays, the wavelength lambda x is approximately in the range of 10 to the power minus 11 to 10 to the power minus 8 meters. Or we can say that is equal to 0.01 to 10 nanometers. And therefore we can write that the wavelength for X-rays is very much smaller as compared to the aperture width. So because of this, the diffraction condition is not met. Diffraction condition is not met. So therefore no diffraction takes place. No diffraction takes place. So option number D is the correct one. Say option D is correct. Next question. And here it is said that thin slice is cut out of glass cylinder along a plane parallel to its axis. The slice is placed on a flat plate as shown. The observed interference fringes from this combination shall be. So we have to find out what is the behavior of the interference fringe. So we are given the figure. So we have slice which is cut along the plane of the axis, and it is placed on the plane with its cylindrical surface on the support system. So we have to find out the how the interference is going to behave. Okay. So in this condition, we are given that we have a glass cylinder is cut, a glass cylinder is cut, and it is placed with its curved surface on a flat glass. You can say curved surface on a flat glass plate. And so we can say there will be a thin air film that will be between the curved surface and the flat plate, and that is going to vary in thickness across the surface. So you can say the thin air film between the curved surface and flat plate varies in thickness across the surface. Varies in thickness across the surface. And it is also given that the light is normal to the surface. So therefore, the interference is between two reflected rays. So you can say interference is between two reflected rays, and the first ray will be from the bottom of the curved surface. The first will be from the bottom of curved surface or we can also say it as glass to air interface. Glass to air interface. And the second one, it will be from top of the flat plate. From top of flat plate, or we can also say it as a air to glass interface. Air to glass interface. So first of all, let us find out how the thickness of the film, air film, is going to vary. You can say air film thickness, and you can write that the air film thickness let us put that is given as T of x, varies with the position of x along the flat plate. Varies with the position x along the flat plate. And we have a cylindrical surface. So you can say for cylindrical surface, the thickness of the air film at the horizontal distance x from the line of contact. The thickness of the air film at a horizontal distance from line of contact, we can write that approximately will be equal to T of x is equal to x square divided by 2r, and this is approximately, not the exact one. Okay. Where r is the radius of curvature of the, you can say, cylinder, and x is the distance from the line of contact, that is center. So here r is the radius of curvature, of cylinder. Now we know that the interference condition, whether it is constructive or destructive, depends upon two things. First one is the optical path difference, and the other one is the phase change on reflection. So we know that interference condition, and that can be constructive or it can be destructive. Both depends upon two conditions. First one is optical path difference. Sometimes it is also called as a path difference. So we have optical path difference, and second one is our phase change on reflection. Phase change on reflection. Now in this case, the light is from air to glass, and then it is back from glass to air. Okay. So therefore we can say that light reflecting from air to glass undergoes a pi phase shift. undergoes a pi phase shift, and from glass to air does not. And light reflecting from glass to air does not. So net phase difference you can see that net phase difference, let us call that as delta phi, will be equal to, this will be 4 pi t of x divided by lambda, and this comes as plus pi. And the term which is our 4 pi lambda t of x, this is because of the double path through the film. Double path through the film. Okay. And the pi is because of the phase change. So now we can just formulate for it for destructive interference as well as the constructive interference. Okay. So we can write that for dark fringes which is basically destructive interference, we can say that our 4 pi t of x divided by lambda plus pi should be equal to 2m times pi, and this gives us that our t of x will be equal to, this will be m minus 1 by 2 and lambda by 2. Similarly, we can write for bright fringes. So we can say for bright fringes, that is our constructive interference, and for constructive interference we can say that 4 pi upon lambda t of x plus pi should be equal to 2m plus 1 and multiply by pi, and this gives us that our t of x will be equal to m lambda by 2. And then we can find out the what will be the fringe spacing and shape. So we can say fringe spacing and shape, and we can calculate that we already know that our t of x is equal to x upon 2r. So we are going to get that our x of m, that is a fringe space, will be equal to 2rm lambda by 2 and square root, or which will be coming as rm lambda. Okay. So it means the fringe space is dependent upon, so based on this equation we can say that fringe position grows as square root of m. So which basically means that it will be non-uniform spacing. Non-uniform spacing. And non-uniform spacing that decreases outward. That decreases outward. And another thing we can say that our t of x is only a function of x. So we can say our t of x is only a function of x. A function of x. So it means the fringes will be straight line because of the constant and parallel to the cylindrical axis. So you can say the fringes are straight lines or we can say constant thickness lines. Constant thickness lines and parallel to cylindrical axis. Parallel to cylindrical axis. Okay. So therefore, the only option is that the fringes will be straight lines. So the option number A is the correct option. So you can say option A is correct. Next question. It is asked that a quarter cylinder of radius r and refractive index 1.5 is placed on the table. A point object P is kept at a distance of mr from it. Find the value of m for which the ray from P will emerge parallel to the table as shown in the figure. So we are given this figure. So we have a table and a point P, and the final ray which is emerging from this quarter lens should be such that it comes parallel to the table. So this is the final condition and this is the initial condition that of the ray. Okay, so we have to first of all try to find out how the ray is going to behave inside this particular quarter lens, and for that we need to find out what will be the position of the image. And in order to solve it, we have to find out what will be the angle of refraction at the curved surface, and in order to emerge parallel, the refraction angle should be equal to 0 at the curved surface. Okay, so it means somewhere here the angle of refraction should be equal to 0. So first of all, we are going to find out the image position. So we say that the things which are given to us, let me write it. First of all, we are given that radius is given as r and refractive index is 1.5. Okay, so we can use just directly first of all we are going to use the, you can say, formula for finding out the refraction at this plane surface. Okay, let us suppose this point is called as B. So we can say that refraction at point B on plane surface So we can use the formula mu2 upon V minus mu1 upon U is equal to mu2 minus mu1 upon R. R1 let us call it, for to differentiate it from R. We are given that mu1 is our 1, we are given that our mu2 is our 1.5, and the position of the object, that is U, is given as mr, and that will be our minus R. And here it is you can say plane surface, so our R1 will be equal to infinity. So we can say 1.5 divided by V minus 1 upon minus mr is equal to 0, and this gives us that our V will be equal to minus 1.5 times mr. So we found out the position of the image, and the position of the image is on the same side that the position of the object because of the negative sign. So we can just draw the approximate figure for that. So we have this vertical surface, and we are given an object. Let us suppose that object is somewhere here, and this is our curved surface. So the ray striking this point B, and it will be something normal here, normal will be like this, and ray, it says that this is my object and the image is on the same side because of negative sign. So this image will be a virtual and it will be forming in the same side. So this will be my image. Let us suppose we are calling it as I1. And if we further extend it, so it will be, the ray will be going something like this. And from here we are supposed to that it should be actually traveling parallel in this way. So we found out that this distance is our 1.5 times mr. And for object we have the distance of mr, and the radius is given as r. Now this, you can say, the image that is formed by the plane surface will act as object for the curved surface. So this, it should be actually different. It should be forming a straight line actually, like this, and then it will looks good now. Yeah, so this is our A, this is B, and let us call this as point as C. So we can say the image, the virtual image, the virtual image I1 formed by the plane will act plane surface will act as the object for the curved surface surface. So therefore, we can say that the distance of the object from the curved surface which is basically our I1 from the curved surface let us call that as u prime, and that u prime will be equal to we just found out our v, and that will be plus r. V is our minus 1.5 times mr, and this is our plus r. So we are going to get this as that of r will be equal to 1 minus 1.5 times m. And now we can use the refraction formula at the curved surface at point C. And say for point C at curved surface, we can write that our mu2 upon v prime minus mu1 upon u prime will be equal to mu2 minus mu1 upon r2. And here mu1 will be equal to 1.5, mu2 will be equal to over 1, and our v1 prime will be equal to infinity because emergent ray is parallel, and our r2 will be equal to minus of r. So we get this as 1 upon infinity minus v u prime we just found out is our 1.5 divided by r, 1 minus 0.5 m is equal to 1 minus 1.5 divided by minus of r. And if we solve it, we can get that our m will be equal to 2 upon 1.5, and this can be also written as 4 upon 3. So this is the value of m which we were supposed to find out. We come to the next question. And in this question, it is asked that the xy plane is the boundary between two transparent media. Medium 1, which is z greater than or equal to 0, has a refractive index of square root of 2, and medium 2, which is z less than or equal to 0, has a refractive index of square root of 3. A ray of light in medium 1 given by vector A 6 square root of 3i plus 8 square root of 3j minus 10 unit k vector is incident on the plane of separation. Find the unit vector of the direction of the refracted ray in medium 2. So we are given basically two mediums, 1 and 2, and their respective index, and we have the incident ray vector. Okay. In this case, we are going to use Snell's law, and then we are going to define the plane of incidence by the incident ray and the normal to the surface. And the refracted ray lies in the plane of incident, and that is going to give us the unit vector in terms of the, and more or less in this case we are going to use the basic property of, you can say, the vectors in order to get the solution. And in the first part we are going to find out the angle of incident, that is our theta 1. Angle of incidence, which is our theta 1, and for that we are going to first of all find out its magnitude, and then we find out the angle by using the you can say cosine of the angle. So we can write that the magnitude of vector A will be 6 square root of 3 square plus 8 square root of 3 square plus minus 10 square and its square root. So this will be coming as 108 plus 192 plus 100, and so we are going to get our magnitude will be equal to square root of 400, giving us it as a 20. Now we are going to find out the cosine of angle of incident. Cosine of angle of incidence, and this is A is basically vector, so we can use the vector property for the cosine angle. You can say the cosine of theta 1 will be equal to our vector A into k unit vector divided by vector A magnitude and minus k and its magnitude. So this gives us that our vector A dot k unit vector, I and j will be coming as 0, only thing will be left is our k, and that will be our 10, and the magnitude we just found out is our 20. So this comes as 1 by 2, giving us that our theta 1 will be equal to 60 degree. So we found out the angle of incident, that is our theta 1 was 60 degree. Now we are going to find out what will be the angle of refraction if we suppose that is our theta 2. For that we are going to use Snell's law. Snell's law, and we can say n1 sine of theta 1 is equal to n2 sine of theta 2, and we substitute the value. n1 is given as square root of 2, theta when we just found out is sine of 60, and n2 is given as square root of 3, and here we have sine of theta 2, and this gives us the sine of theta 2 will be equal to 1 upon square root of 2, giving us that our theta 2 is equal to 45 degree. So we found out the angle of incident as well as the angle of refraction. Next we are going to find out what will be the components of unit vector along the incident ray. Component of unit vector along the incident ray. along the incident ray. So we can write, suppose that unit vector is our A unit vector, and that will be equal to vector A and divided by its magnitude. So we get this as 6 root 3 divided by 20I, and this will be plus 8 root 3 divided by 20J minus, and here we have 10 divided by 20, and this is our K unit vector. So we get the unit vector A, and this will be equal to this will be coming as 3 root 3 divided by 10 I unit vector, plus we are going to get this as 2 square root of 3, and this will be our 5 J unit vector minus 1 by 2 K unit vector. And it is, the refractive ray basically lies in the plane of incident. So we can write its direction vector in terms of the using two coefficient alpha as well as beta. Then we are going to find out the value of alpha as well as the beta. We can say that the refracted ray lies in the plane of incident, in the plane of incidence. Therefore, its direction vector can be written as, you can write its direction vector as R unit vector will be equal to alpha. We have A cap, its parallel vector plus parallel unit vector, and we have this as beta and with the K unit vector. And this parallel unit vector rather, is the projection of a unit vector onto the xy plane, So we can find out our A unit vector. So A parallel unit vector rather will be equal to, this will be 3 root 3 divided by 10, and it comes as I unit vector plus 2 root 3 and divided by 5, this is our J unit vector. And now we are going to find out the value of alpha and beta. So here alpha and beta are constants whose value we are going to find out. Okay. And the R unit vector makes an angle of 45 degree with the normal, that is our K unit vector. So our R unit vector makes angle of 45 degree with normal, that is our K unit vector. So we can write cos of 45 will be equal to, we have our R unit vector dot minus K unit vector divided by R unit vector magnitude and multiply by minus K unit vector its magnitude. So this will be coming as minus of beta divided by 1, and cos of 45 is our 1 by square root of 2. So therefore, we can write our beta can be written as, this will be minus and 1 by square root of 2, or we can also write it as minus square root of 2 divided by 2. And we also know that the magnitude of projection of r unit vector onto the xy plane is sine of 45 degree. So we know the magnitude of the projection of r unit vector on to the xy plane is sine of 45 degree. Therefore, we can write alpha multiplied by unit vector parallel magnitude will be equal to sine of 45. So we substitute the respective values, or let us first of all find out the A parallel unit vector. So we get A parallel unit vector will be equal to, we have this as 3 square root of 3 divided by 10 whole square plus 2 square root of 3 divided by 5 and its whole square, and we get this as square root, and this gives us close to, it will be coming as square root of 3 divided by 2. Now we substitute the value, we get alpha into square root of 3 divided by 2, and we have sine of 45, that will be equal to 1 upon square root of 2, and this can be written as square root of 2 upon 2. Therefore, we get alpha will be equal to square root of 2 divided by square root of 3. So we found out the value of alpha as well as beta. So we can say the direction vector of the refracted ray of a refracted ray, and that can be written as r unit vector will be equal to, we found just it as square root of 2 divided by square root of 3, and it will be product of just pause our a unit parallel, that is our 3 square root of 3 divided by 10 I unit vector plus 2 square root of 3 divided by 5 j unit vector, and minus, that is our value of beta, and we can say minus square root of 2 divided by 2, and we have this a k unit vector. Thus we get our r unit vector will be equal to 3 square root of 2 divided by 10 I unit vector plus, we have here 2 square root of 2 divided by 5 j unit vector minus square root of 2 divided by 2, and we have a k unit vector. So it means the unit vector in the direction of refracted ray in medium 2, you can say this is the unit vector in the direction of the refracted ray in medium 2. Okay. So this is our final answer for the unit vector. Okay. So this question we solved mostly by using the properties of the vector. Okay. Next question. And it was asked that the Young's double slit experiment is done in a medium of refractive index 4/3. A light of 600 nanometer wavelength is falling on the slits having 0.45 millimeter separation. The lower slit S2 is covered by a thin glass of sheet of thickness 10.4 micrometer and refractive index 1.5. The interference pattern is observed on the screen placed 1.5 meter from the slits as shown in figure. All wavelengths in the problem are for the given medium of refractive index is 4.3. Ignore the dispersion. So this is a basic figure. We have two slits S1 and S2. S2 is covered by, you can say, sheet, and this is the screen. So based on this we have three questions. Find the location of the central maxima, that is bright fringe with zero path difference on the y-axis. Find the light intensity of point O relative to the maximum fringe intensity. And the final last one is, now if 600 nanometer light is replaced by a white light of range 400 to 700 nanometer, find the wavelengths of light that from maximum exactly at point O. In this case, we are given that so this question we can say, okay, so screen has a refractive index of 1.5 and the entire medium, rest medium, is having a refractive index of 4.3. Okay. So first of all, let's find out part A, that's the location of central maxima. So we have part A, location of central maxima, and because of sheet S2 that's placed over S2, it will be introducing a path difference, optical path difference due to glass sheet. Okay. So you can say optical path difference due to glass sheet over slit S2. Let us call that as delta x2, which will be given as refractive index of glass, refractive index of medium -1, and multiply by its thickness. And we can also say the geometrical path difference due to vertical fringe width. So we can say that geometrical path difference due to vertical fringe shift. Vertical fringe shift, and let us call that as delta x1. So delta x1 will be equal to y d, and capital D. Okay. And we need that the path difference should be equal to 0. So let's put equation 1 and this is equation 2. So if the path difference is to be 0, these two terms should be equal. You can say that for central maxima, to shift back to 0 path difference, equation 1 should be equal to equation 2. So we equate both equation, we get yd upon capital D is equal to refractive for glass for medium minus 1 multiplied by T. So from here we get that our y, that will be our shift, will be equal to mu g mu m minus 1 and we has T capital D divided by small d. Now we easily substitute the values. We get this as the shift, which is our y, will be equal to we have mu g is our 1.5, medium is given as 4 by 3 minus 1 and thickness T is given as 10.4 into 10 to the power minus 6, distance is given as 1.5 and small d slit 4.5 into 10 to the power minus 3, and this gives us that it will be equal to 4.33 millimeters. Okay, so it means central maxima shift by 4.3 in the downward direction. So you can say central maxima shifts by 4.33 millimeter downward. Now we have to find out the intensity at point O, which was our original central point. So we have part B now. Intensity at point O, which is our original central point. Original central point. So at point O, the path difference is purely due to the glass sheet. You can say that at point O, the path difference is purely due to glass sheet. So we can write that our delta x will be equal to mu of g mu of m minus 1 and multiply by t, and substituting the values we get this as mu of g is 1.5 and this is 3 by 4, 4 by 3, 4 by 3 minus 1 and thickness is given to us as 10.4 into 10 to the power minus 6 and this comes as 1.3 into 10 to the power minus 6 meters. Now we find out the path difference, sorry, phase difference. Path difference found out. So we get the phase difference, suppose that is phi, will be equal to 2 pi lambda m multiplied by delta x. So we get 2 pi, wavelength is given as 6 into 10 to the power minus 7, delta x we just found out is 1.3 10 to the power minus 6. So we get that our phase difference phi will be equal to 13 by 3 and pi. And we already know the formula, which is that our I is equal to our I max cos square of phi by 2. So we get this as our I max cos square. Phi we just found out is 13 pi by 3. So this comes as 13 pi by 6. And this we can say that our, we can write that this implies that 13 pi by 6 should be equal to 2 pi plus pi by 6. We just manipulate it. So this gives us that cos of 13 pi by 6 will be equal to cos of pi by 6, giving us square root of 3 divided by 2. And this tells us that our I will be equal to I max cos square. So this gives us 3 by 4. Okay. So therefore the intensity at O is 3 by 4 of max. You can say that intensity at O is 3 by 4 times the maximum intensity. And finally, we are going to find out for the white light ray what will be the range for maxima at O. So we come to the part C. In part C, we are going to find out the wavelength of white light that form maxima at O. And we already know that our delta of x we just calculated is 1.3 into 10 to the power minus 6 meters. And maxima, it means the constructive interference. So we can say for constructive interference, our delta x should be equal to n times lambda, where lambda is the wavelength. Okay. So we can say that our lambda will be equal to delta x is our 1.3 into 10 to the power minus 6 divided by n. So one by one we are going to take the various value of n and try to find out what will be the lambda which actually forms in the visible range. So we can say that for n equal to 1, this gives us lambda is equal to about 1300 nanometer. For n is equal to 2, lambda will be equal to 650 nanometer. For n is equal to 3, gives us lambda is equal to 433.33 nanometer. And for lambda is equal to 4, we get, n is equal to 4, lambda will be equal to 3 to 5 and nanometer. And for visible range, the wavelength should be between 400 and 700 nanometer. Okay. So we have only two values which come within this particular range, and this is our these two values. Okay. So we have 650 nanometer and 433.33 nanometer. So we can say the wavelengths are So the wavelengths are 650 nanometer and 433.33 nanometer, because we have to fix it within the visible range. I think this completes the question. Yes. So these were the questions which was asked in the year 1999. So this completes all the questions. Thank you.